Okay, so good morning to all. We are discussing CPU scheduling algorithm. So we have seen the four CPU scheduling algorithms, that is first come first serve, SJF, priority scheduling, and round robin. So we will see few more examples based on this algorithm, right? And if you have any doubt, you can clear it. So these examples I think I have given you for the homework. So let us see how many of you got the correct answers. Okay, this is the example, contains 5 process. P1, P2, P3, P4 and P5. Arrival time is given 0, 1, 2, 3, 4 and burst time is 9, 1, 7, 1, 6, right? So we have to find out the algorithms are, which are the algorithms given in the question? FCFS, first come first serve, and SJF, and FCFS. So first we'll see with FCFS. So starting from here, starting from 0, we'll go. So first arrival time of each process is considered here, right? Arrival time of the process P1 is 0. So if we start to draw the Gantt chart, right? So here we'll see. Suppose it is a time axis T. Start our start our process at 0. So at zeroth time instant, how many processes are available in the system? Only one process, that is P1 is available at 0. P2 is arrive at 1 millisecond. So 0, you cannot say that at 0. So P2 is available at 1 millisecond. Then P3 arrival at 2 millisecond, right? P4 arrive at 3 millisecond, right? So 3 millisecond, and P5, right? P5 arrive at 4 milliseconds. So here I can say that this is nothing but your P5 process. This is nothing but your P4 process, right? Then your P2 process, and this is your P1 process arrived in the system. And this is, see, this is general, this is the way how the processes arrived in the system. Getting this point? All of you clear this point? So the system is started at 0 time instance, but if we say at 0th millisecond, only one process, that is P0 process, was present. Then after 1 millisecond, the process P1 arrived in the system. Then P2 arrived at 2 milliseconds. Then P3 arrived at P3 arrived P1. Sorry, this is the P1. This is P2. Sorry, P3, P4, and P5. 1, 2, 3, 4, 5. So P3 arrived at 2 milliseconds. P4 arrived at 3 milliseconds, and P5 arrived at 4 milliseconds. This is the scenario. All right. So if we are following, the FCFS policy, so I start taking the P1 process, and execution, and P1 will execute up to how long? It will execute up to 9 milliseconds. P1 process start executing up to 9 milliseconds. So 0 to 9. So I can mark here. 0 to 9. For example, 0 to 9 milliseconds here. P1 start executing, right? So this is the way. 0 to 9 millisecond, P1 start its execution. Now, so up to 9 millisecond, all these processes are arrived in the system already. Up to 4 milliseconds. So for here, so all processes P2, P3, P4, and P5, they all are present in the system. No doubt about it. Yes. So they can be executed from here. Like here, you can take here P2, and P2 starts its execution. From here up to 1 millisecond. So 9 to 10. Then P3 is taken for the execution. So P3, the execution time is P3 execution time is 7. So 10 plus 7 is equal to 17, right? And then it will go for the P4, and P4 executes for how long? P4 only 1 millisecond. So 18, and finally the P5 executes up to, and the execution time for the P5 process is 6. that is nothing but 18 plus 6 is equal to 24, right? So this is the way how we are drawing the Gantt chart, right? This is the way how we are drawing the Gantt chart for the FCFS policy, right? Now finding out the arrival time, we have to subtract, finding out the waiting time, we have to subtract arrival time, right? So for P1, so if I write for P1, that is equal to 0 minus 0, 0 minus 0, that is equal to 0, right? So this is waiting time for P1 is 0 because P1 arrived at 0 and start its execution at 0. So there is no waiting for the P1 process. Clear this? Now P2. Now for P2 process, if we see here for P2 process, P2 has arrived in the system at 1 millisecond. So minus 1, you just write here minus 1, that is equal to. And when P2 is completely executed, P2 starts its execution at 9th millisecond and executed completely during this slot 9 to 10. This slot it has got execution 1 millisecond, right? So up to 9 milliseconds. So I can say that 0 to 9. So this is the way, but it has arrived at 1 millisecond. It has arrived at 1 millisecond. So 1 to 9 is only the waiting time for the process P2. Clear this point? So waiting time, because P2 arrived at 1 millisecond here. So this 1 to 9 only, that is the only waiting time for the process P2. So I can say that 9 minus 1, that is equal to 8 milliseconds. Clear? For P3. So P3 is completely executed between this 10 to 17 slot. So I can write here P3, that is equal to 10 minus arrival time for P3 is 2 milliseconds. So P3 arrived at 2 milliseconds. So this is only, see carefully from this diagram, this is, it may not be very clear to you, but just try to understand from 2 to 10, that is nothing but 8 milliseconds it has to wait. What we are finding here, we are finding out the waiting time for the process. So arrival time must be subtracted for finding out the waiting time. Remember this point. Then P4 that is equal to, so P4 executed, start executing from 17 minus 17 minus arrival time is P4 is 3, that is equal to 14, right? 14 is the waiting time, and for P5 18 minus 4 arrival time, that is equal to 40. So add all these things, the addition come out to be 44, and you are getting here average waiting time for all the 5 processes with the help of your FCFS policy. So I think all of you get the same answer. This example you have to solve. You're supposed to solve in the home as a homework assignment, right? But anyway, so this is the AWT and ATT, same way you can find out. So for ATT, waiting time plus the waiting time and execution time, you are getting the turnaround time for that particular process, right? Now see the next option, or see here next algorithm, that is the SJF. So I think you may have problem with SJF, right? So for SJF, again the same case. So 0, then 1, then again 2, right? Then again 3 and 4, right? So here P1 process arrived in the system, then P2 process arrived in the system, then P3 process arrived, P4 arrived in the system, and P5 arrived in the system. So this is the arrival time of each and every process. Now this is the HJ policy, right? This is the HJ policy. See carefully. And for this HJ policy, what we have to do here, we have to apply the, we have to compare their execution time, and also we have to consider their arrival time. Means these two factors, and means addition in the sense logical and means there are two conditions, that is nothing but execution time plus arrival time, that we have to consider. So how to consider this thing? So execution time for process P1 is 9, execution time for P2 is, say for example 1, see here, then P3 is 7, then P4 is 1, and P5 is 6 milliseconds. Clear? So, but here if we want to compare P1 at 0th millisecond, there is no other process available in the system. Are you getting my point or not? When I start the system at 0th millisecond, SJ, what is the SJ policy? SJ policy says that you have to compare between the execution time of the process and the process having the shortest execution time, that will go for the execution. Clear? This is the logic behind the SJ. But the question is about arrival time. Meaning is that P1 is the only process present in the system, and there is no other process for the comparison with the P1 process. right? So as there is no other process for the comparison, so I draw this here. So at 0th millisecond, say for example at 0th millisecond, there is only one process, and that is P1 process. So by default, P1 is taken for the execution, because there is no comparison between the execution time, because the P1 is the only process, right? When the comparison start at 1 millisecond, because at 1 millisecond the second process arrived, that is called as the P2 process. So P1, so at this particular instance, if I draw the, suppose P1, how many milliseconds are remaining here for P1? P1 has executed already 1 millisecond, and 8 milliseconds are still to go for the P1 process, right? For P2 is equal to 1. Now you can compare between this 8 and 1 here at 1 millisecond. Getting my point or not? You can compare, because at 1 millisecond you have the two processes in your hand, means operating system has the two processes in his hand. P1 is equal to 8 and P2 is equal to 1 millisecond. So comparison takes place here. So P2 is taken for the execution, and that is called as your preemption. That is called your preemptive SJF. PREEMPTIVE, right? Preemptive SJF. Sorry, SJF, right? So this is the way. Why? Because the newly arrived process, which is the newly arrived process, P2 is the newly arrived process having the shortest burst time, CPU time, as compared to the currently executing process. See carefully, very carefully, right? That's why the P1 is removed from the processor and P2 is taken for the execution. Clear? I'm repeating the same statement. At again repetition, see carefully, listen carefully. At 0th milli instance, though we have to follow SJF policy, but SJF policy says that you have to compare the execution time of the two processes, right? But there is no comparison, there is no other process for the comparison. How many processes are there? There is only one process, and that is called as the P1 process. So what we have to do here, P1 is the only process, and by default it will go for the execution, P1 process. Now at 1 millisecond, P1 is currently in a running state. And P2 process arrived. So if we see the scenario, this is the scenario at 1 millisecond. P2 remaining 8 milliseconds still for its execution, and P1 remaining 8 milliseconds for execution, and P2 is equal to 1. P2 is the newly arrived process and P1 is the currently executing process. So we can say that the newly arrived process P2 having the less CPU execution time as compared to currently executing process. That's why the current executing process, that is P1, is removed from the processor and the newly arrived process is assigned CPU for the execution. This is the exact logic, right? And it will continue up to how long? It will continue up to next arrival of the process. So next arrival of the process is at 2 milliseconds. So at 2 milliseconds. So what is the scenario at 2 milliseconds? So I'll draw here the scenario at 2 milliseconds. So at 2 milliseconds, how many processes are there in the system? So there is a P1 that is equal to 8 milliseconds to go. Then P2 is equal to how many time it executed? So how much execution? 1 millisecond, and its execution time is 1. So P2 is 0, means there is no need for P2 because P2 is completely executed. And the next process arrived, that is equal to P3, and that P3 is equal to how much is the execution time? P3 is equal to 7, right? So this is the scenario at second millisecond. See carefully, yeah. Scenario at 1 millisecond is only one process. P1 is equal to 8. P1 is equal to 9 at 0 millisecond. At 1 millisecond, P1 is equal to 8 because 1 is already executed, and P2 newly arrived, that is equal to 1. Now at second millisecond, P1 is equal to 8 as it is. P2 is equal to 0 because P2 you have assigned new process for the execution. That's why it is completely executed 0 millisecond, and new process arrived at P2, that is called as nothing but your, and it is having the execution time is equal to 7. Now this is the picture. At the second millisecond. Getting my point or not? So this is the picture at the second millisecond. That's why what we are going to do here, we are going to again comparison between 8 and 7. 0, there is no question about the comparison. We compare between 8 and 7. So definitely see again the statement. Again, see my statement carefully. The newly arrived process P3 having less CPU execution time as the currently executing process, that is nothing but P1. So again comparison between P1 and P2. So P3 is assigned CPU for the execution. P3 is now assigned CPU for the execution. So you may ask the next question, how long it will execute? So we have to check it again, next arrival time. Which is the next arrival time? Next arrival time is 3, for example. Next arrival time is 3. So scenario, I'll write here scenario at third millisecond. So scenario at third millisecond, I write here. So how many processes are there here? So at third millisecond, I can write here P1 is equal to 8, right? Then P2 is equal to 0, P2 is equal to 0. Then P3 is equal to 6 because 1 millisecond is already executed for P3, and new process arrived. It is called as the P4 process, and P4 comes with how much execution time is required. That is equal to 1. Now this is the picture. This is the picture at third millisecond. This is the picture at third millisecond. All of you see it carefully. Now at third millisecond, I have the 4 processes for the comparison. The P1 requires 8 milliseconds for execution. The P2, no need of execution, is already executed. P3, 6 milliseconds are required, and P4 process require 1 millisecond. Now here you can follow, here you can apply the SJF. And SJF says that out of these 3 processes, which is having the shortest burst time? P4, 1 millisecond. So P4 is assigned execution, not P3 and not P1, but P4 is assigned for execution or CPU, right? So P4 will execute up to how long? So you may ask the question, it will execute up to how long? Up to next arrival time, and next arrival time is 4, for example, right? So because out of 8, 6 and 1, P4, the newly added process having the shortest execution time as compared to all other processes, that's why the newly added process get the CPU for its execution, right? And we have to check again at 4th millisecond. So again at 4th millisecond, we will write down the scenario. At 4th millisecond, the P1 is there in the system, is equal to how much millisecond it has to require for execution? 8 milliseconds. So no question about P2. I will not write here. P2 is equal to 0. P3 is equal to 6. Then P4 is just executed completely, and its execution time is 1 millisecond, and 1 millisecond is completely executed. So P4 is equal to 0, and new process arrived at 4th millisecond. New process arrived at 4th millisecond. So P5, and that process requires how much is the time? 6. Clear this point? So at 4th millisecond, this is the scenario. This is the scenario at 4th millisecond. How many processes I have? I have these 4 processes: P1, P3, P4, and P5. P2 is already executed. So 8, I can compare between 8, 6, and this 6. I can compare between 8, 6, and 6. SJ, shortage job first. Which is the shortest? So here P3 and P5 are the same shortage job. So which will go first for the execution? Of course, P3 will go, because if the execution times are same, it will follow the FCFS policy. First come, first serve policy. So P3 will go for the execution. So I mark here P3. And how long it will continue its execution? So as there is no other arrival point, it will continue up to its full execution, that is equal to 6 milliseconds. So 4 plus 6 equal to 10, right? So it will execute up to 10 milliseconds because there is no other process. See here, why? Because there is no other process arriving in the system after 4 milliseconds. So definitely it will execute up to, because it is the shortest one. So definitely it will execute up to 6 milliseconds. So P3 completely execute, and then P5 is taken up to 16, right? And finally you are going to take the P1 process, and P1 execute from 16 to 16 plus 8 that is equal to 24. P1 execute as the last. And this is the way preempt to SJ work. This is the way how we can solve the numericals on the preempt to SJ. Getting my point or not? See once again carefully. Arrival time. See carefully. Again, I am repeating the same thing. Listen it carefully. Arrival time. We have to consider the arrival time of the process. So arrival time is 0. For example, this is the 0th arrival time. How many process? So we have to draw a picture at every arrival time. We have to think of the processes which are available at each arrival time. So 0, only one process, P1. So no any other process. So directly P1 go for the execution. Simple one. Now at 1 millisecond. What is the picture? So picture says that there is a P1 remaining 8 milliseconds, and new process P2 that is equal to 1. So you have to switch. You have to context switch between the processes P1 to P2. So P2 is taken for the execution and P1 will be in a waiting state. And up to how long it will continue? Up to second millisecond, because the next process arrived at 2 milliseconds. So 2 milliseconds. So see the scenario at the 2 milliseconds. So 2 milliseconds P1, P2 and P3, because third process arrived, P3 process arrived. P1 is 8 milliseconds, P2 is completely executed, and P3 is equal to 7 newly arrived process. So as this is having the shortest, 7 is less as compared to 8. P3 is taken for the execution up to 1 millisecond. Because at third millisecond, again the new process arrived. And so why we are checking? So we have to check at arrival of each process. We have to check at the arrival of each process. So third millisecond, so what is the scenario? Again, we write down here process P1, 8 milliseconds to go, P2 is equal to 0, P3 is equal to 6, because 7 minus 1, 1 millisecond is already executed, 6, and P4 is equal to 1, and P4 is the newly arrived process. So after comparing between 8, 0, 6, 1, so P4 will go for the execution, and after how long it will execute? Up to 4 milliseconds here, because at 4th millisecond, the next process arrived in the system. So that's why, so 4 milliseconds, again I draw the scenario at the 4th millisecond, P1 8, P3 6, P4 0, and P5, which is the newly arrived process, that is equal to 6. Getting this point? So comparison 8, 6, 6, so 6 and 6 are equal, so again I have to follow here FCFS, so I will go for a P3 process, and P3 is assigned to the system. Now how long P3 will continue? P3 will continue up to, in total its duration, complete execution up to 6 milliseconds, because after 4 milliseconds, there is no process arrived in the system, there is no chance for any new process, no comparison. So it will continue up to 6 milliseconds. So this one will continue, then P5 is taken, and finally the P1 will be taken for the execution. This is the simplest logic behind SJ preemptive. Get this point? So in this way, so just clear this. Right. Now drawing, so finding out the waiting time. So waiting time for P1. So P1 is taken from here and it is completely executed within this particular slot, P1 process. So waiting time for process is nothing but 16 minus arrival time. That is equal to 16 minus 1 minus 0. Here 1 is missing. So 16 minus 1, because this one is nothing but its execution time. So this you have to minus. So 16 minus 1 minus 0, that is equal to 15 is the waiting time for the process P1. P2. P2 is start executing here, it completely executed between 1 to 2 slot, and arrival time is also 1. So 1 minus 1 is equal to 0 is the waiting time for the process P2. P3. P3 completed its execution between this slot 4 to 10, and arrival time for the, so 4, I can say here 4 minus arrival time is 1, right? So 4 P3 process 4 minus 1 minus 2, because P3 starts executing between this particular slot 4 to 10, that is the 6 millisecond, and before that it has executed 2 times. So 4 minus 1 minus 2, that is equal to 1. P4 process, P4 start executing between 3 to 4, and arrival time is 0. So arrival time for the P3 process is 0. So something is wrong here in this case. So 3 minus 0 is equal to 3. It is wrong. And P5, for P5 process, it starts executing from 10 to 16. 10 to 16. And arrival time for P5 process is 4. So that's why 10 minus 6 is equal to 10 minus 4 is equal to 6. So finding out the waiting time for the process, and we have to find out the average waiting time in this way. Now, once the waiting time of each process has been found out, so add up the execution time, we will find out the turnaround time for each process, and finally the average turnaround time for each process. Getting my point? Getting this thing? Okay. Okay, so see the next example. So in this example, P1, P2, P3, P4, P5 are given, and arrival time is different here, 0, 1, 3, 4, 6, and the execution time is 8, 5, 3, 1, 4, 8, 5, 3, 1, 4, and HJF is given. We have to find out with HJF, and which is the next one, round robin TQ equal to 2, round robin TQ equal to 2, right? So we'll see with SJ. I'll draw here Gantt chart. See carefully, yeah. 0, Arrival time 0, only one process P1 is present in the system. P1 is taken for the execution at 0th millisecond and it will continue execution up to 1 millisecond. Right? Now at 1 millisecond, the next process arrived, that is equal to 5. And here P1 is equal to, now here P1 is equal to how much? P1 is equal to 7 and P2 is equal to 5. So next process, P2 is taken for the execution. P2 is taken for the execution. See here. P2 is taken for the execution and it will continue up to 3 so how 3 milliseconds. So I can mark here 3. So at 3 milliseconds, P1 is equal to still P1 is equal to still 7 milliseconds to go. Then P2 is equal to, so minus 2 minus equal to 3 still remaining, and P3 process arrived. P3 is equal to 3. So which process will go here? See, now here tie, or here the two execution time are same. P2 is equal to 3 and P3, which is the newly arrived process, that is equal to 3. So which will go? So your, because P2 total time required is 5, but between 1 to 3, 2 milliseconds are already executed. From 1 to 2 and 2 to 3, 2 milliseconds executed. So it will continue in execution. P2 process continue in execution up to 4 milliseconds. Up to 4 milliseconds. So here, so I can have P1 is equal to 7 here, right? Then P2 is equal to 2 because 1 millisecond is executed. Then P3 is equal to 3, and next process P4 arrived. P4 arrived. That is equal to P4 is equal to 1 at 4th millisecond. At P4 arrived at 4th millisecond, right? This is the arrival time. So see now the comparison 1 and 2. Now here compare between 1 and 2. Right. So P4 is taken for the execution. P4 is taken for the execution, and it will execution time is only execution because 1 is less as compared to 2. So and it will continue up to next millisecond and 6. But it will not go to 6. It will not go to 6 because its execution time is only 1 millisecond. So at 5 only the P4 process completely executed. At 5 only the P4 process is completely executed. So scenario at P5, so P1 is equal to 7, right? Then P2 is equal to 2 and P3 is equal to 3 and P4 is equal to 0 and P5 is not arrived in the system because arrival time for the P5 is 6. P5 is not still arrived in the system because arrival time for P5 is 6. So out of this 1, 2, 3, which will go? P1 will, sorry, this is 7. No, this is 7. It is not 1. 7, 2, 3, which will go? So P2 go for the execution because 2 is the less, and it will check at 6. So what is the scenario at 6 milliseconds? So P1 is equal to 7 here at 6 milliseconds. Then P2 equal to 1 millisecond is executed. So P2 is equal to 1 remaining. Then P3 is equal to 3. P4 is completely executed. And the next fifth process arrived here and execution time is equal to 4. Right? So definitely P2 is less. So P2 continue execution up to 7 milliseconds. Getting my point or not? So this is the correct, one can say Gantt chart. Right, now we will again start from here, 7. Now at 7th millisecond, so at 7 millisecond, P2 is completely executed. So only P1, P3 and P5 are the 3 processes available in the system. And as the P3 is having the shortest one, so P3 will go, P3 will continue 3. So 7 plus 3 is equal to 10. Then finally P5 will go, and that is nothing but your P5 is equal to 4. So that is nothing but 14. And last P1, that is equal to 14 plus 7, that is equal to 21. Right. So this is the way. This is the way how to draw the Gantt chart. So you can draw this correctly. Right. So this is the scenario at the 6th millisecond. This is the scenario at 6 millisecond. This is for 5th millisecond. This is for 4. This is the 3rd. This is 1. And at P0, there is only one process, that is equal to 8. That is equal to 8. Now waiting time for process P1. So P1 is executed completely executed between this particular slot. See carefully. 14 minus. Now before reaching to 14 millisecond, is there any slot? Slot it has got executed? Yes. So P1 executed between 0 to 1, this particular slot. So you have to minus 1, right? Because it is execution time, so you cannot call it as a waiting time. And arrival time for process P1, that is equal to So waiting time for process P1 is equal to 13, right? For P2, waiting time for process P2. Now P2, where is the P2 process completely executed? So between this slot 5 to 7, P2 has got completely executed. So I can say 5 minus. So before reaching to this 5, how many times it has executed? So between slot number 1 to 4 means 1 to 4 means 3 milliseconds it has got complete execution. So that is nothing but 3 minus. So this is this one, this one. This cannot be considered 1 to 4. It is the execution time for the process P2. So this is the execution time for the process P2. So 1 minus 4, that is 4 minus 1, that is equal to 3. So 3 is 3 milliseconds we are subtracting here. So 5 minus 3, and arrival time for the P2 is, arrival time for P2 is 1, that is equal to 5 minus 4 is equal to 1 here. Getting my point or not? Then next is nothing but your P3 process. P3. So when P3 is completely executed between the slot 7 to 10, and the earlier to 7 it has execution? No, earlier to 7 it has not executed anywhere. But so that's why we have to only consider the arrival time for P3, that is equal to 3. It comes out to be 4 milliseconds. For P4 process, that is equal to P4. P4 is executed in which slot? 4 to 5. 4 minus earlier to 4. No, there is no execution between earlier this one thing. Only arrival time for P4 process is 4. So I can have the waiting time is equal to 0. And P5 process. And finally the P5 process. P5 is completely executed between this 10 to 14. So 10 minus earlier to 10, whether the P5 executed? No. So only arrival time subtraction, that is equal to 6. That is equal to 4. So add up this 13 plus 1, 14 plus 4, 18 plus 4 is 22. Right, 22 divided by how many is the process? 5. So 4.4 is the average waiting time. Here is answer is wrong here. I don't see answer here. So the calculations are wrong here. So 4.4 milliseconds are the this is nothing but the average waiting time for the process, right? And so accordingly you can find out the average turnaround time for the process. Average turnaround time is nothing but the addition of the waiting time plus execution time. Will get here turnaround time, and with this way you can find out the average turnaround time for the process. Getting this point? I think it is clear. It is very much clear to all of you, right? Now next is nothing but your round robin, where the time quantum is equal to 2. Time quantum the same way we have to take here. First arrival time we have to always consider 0 to 1 take equal to 2. But if the process is having, if the processes they are having the less execution time as compared to 2, the process will execute. Yeah. So 0 P1 is only the process, so P1 is taken for the execution at 2 millisecond at up to, and it will continue up to 2 milliseconds. So at 2 milliseconds, yes, P2 process are at 1 millisecond. So yes, P2 is available. So P2 is taken for execution and it will continue up to 4 milliseconds because TQ equal to 2, time quantum equal to 2. So that's why up to 4 milliseconds it will continue. P3 has arrived at second millisecond. P3 has arrived at second millisecond. So P3 is available. Here we are not going to consider the execution time of the process. We don't have to bother whether the execution time is less or more. We are only considering the time quantum expires or not. So yes, time quantum expires. P3 is taken for the execution, then P4 is taken for the execution, and P5 is taken for the execution. 6 plus 7, and this is why is 1, because P4 requires only 1 millisecond. So there is no question about the time quantum. Then 7 plus 2 is equal to 9. So P5 executed between 7 to 9. Then all processes are executed at one time. So again P1 is taken for the execution and it will continue up to 2 milliseconds, that is up to 11. Up to 11 it will continue. Then P2 is taken after 2 milliseconds. P3 is taken. Now P3 execute only 1 millisecond because it requires only 2 plus it is execution time is only 3 milliseconds, right? So it will execute between 13 to 14 this slot. So at 14 P4 is not available because P4 is already executed. 0 execution is there. So P5 is taken and it will execute up to 1 millisecond, 2 milliseconds, 14 to 16. Then 16 again. So here again you are going to again start the process P1 again 2 milliseconds, then P2 again 1 millisecond because P2 requires how much? 5 milliseconds. So 2 is completed here. For P2, 2 is completed here. So only one is required here. So that is why 18 plus 1, 19, 1 millisecond. So 2 plus 2 plus 1, 5 milliseconds execution time for P2 is completed. And so only remaining process is P1. So rest of the time 19 remaining, whatever it may be at the time, it will execute. It will execute, right? So 19 plus 2, 21. So P1 is 2 plus 2, 4 plus 2, 6 plus 2, 8. So 8 milliseconds is the total execution time required for the process P1, right? Now calculating the waiting time for process P1. So P1 is executed between 19 to 20 slots. So 19. So but before reaching to 19, how many times it get executed? It get executed here P1. So 2 plus 2, 4 plus 2, 6. Then you have to minus 19 minus 6 minus arrival time equal to 0. You have to, it is missing here. Minus 0, that is equal to 13 is the waiting time for the process P1 under the round robin policy, right? For P2. Now P2 is completely executed between the 18 to 19 slots. So 18 to 19 slots. So 18 minus 4. What is this number 4? Means before reaching to this 18, how many times P2 get executed? This is the one slot P2, means 2 millisecond here and 2 millisecond here. So that is nothing but 4 millisecond. Minus it is arrival time. So 18 minus 5, that is equal to 13. Arrival time for the P2 process, right? Then P3 process. Now the P3 process, when the P3 process completely executed between this 13 to 14 slot, so 13 minus 2. So 2, this is the 2, because before reaching to 13, 2 milliseconds it has already executed, and arrival time is 3 for the process P3. So minus 2 minus 3, 5. 13 minus 5 is equal to 8. P4 process. P4 process, when that process is executed completely in which slot? So P4 process executed in this slot, I think 6 to 7, right? Here it is executed. So one can say that 0 and arrival time. So and arrival time is 4. So waiting time is only 2 milliseconds. And P5 is executed between 14 to 16 slot. But before reaching to 14, how many times this P5 executed? So 7 to 9. This is the 2 milliseconds it has executed. And arrival time is 6. This is the arrival time 6. So 2 minus 6, it is minus 8. 14 minus 8 is equal to 6. This is correct way. So you can have the total waiting time is this. Average waiting time is 42 by 5. That is 8.4 milliseconds for the round robin policy. Getting this point? And the turnaround time we are finding out in the way the waiting time plus their execution time, the total turnaround time and average turnaround time, and this is the way. Getting my point? Okay. So this is the way how to solve how to consider the arrival time, how to consider their execution time, and how to find out the waiting time. The important concept. So there is one can say there is no difficulty in this case. It is very simple. It is very easy. There is no rocket science in this particular numerical. Only the thing is that you have to consider the arrival time. You have to apply your logic. You are in the sense you have to apply the logic of that particular algorithm. Whether it is a round robin, you have to apply the logic of round robin. Whether it is a SJ, you have to apply the logic of SJ, or whether it is a priority, you have to assign the priority logic here, and you have to consider the arrival time. So it is very simple, just a numerical calculation between 1 to 9. There is nothing difficult. It is not integration or derivation, just like your M2 or M3. It is very simple. You can solve it very easily and very clearly. Only the thing is that just sit and solve it carefully, right? So next one is, so here we have completed this particular unit. We'll see the unit number 2 is completed here, operating system. So we'll see examples on this particular unit. So before starting to this, just I will. So these are a few examples. First, a numerical is given. So here we have to find out the waiting AWT and ADT for this particular set of processes, right? SJF, it is a one can say non-preemptive SJF. Second example, FCFS policy, then the SJF preemptive, SJF non-preemptive, and the priority as well as the round robin. So 5 algorithms we have to solve here. The third numerical is given. We have to solve for the SJF preemptive as well as the FCFS. And the next example we have to solve this way. Round robin is given here, and the SJF non-preemptive algorithm is given. And finally, the round robin, the next example, question number 5, the round robin policy, find out AWT, ADT, and FCFS. And the next round robin TQ equal to 2 and priority. So we have to practice all these examples so that your concept will be becomes very much clear, and you will have no doubt while solving this example. So if you have any doubt, any query, you can ask me. Okay. Now what we'll do here, we'll just solve a numerical here. You have to take your notebook, you have to take the pen, and you have to start solving the first numerical. And any doubt and any one can say any question, you can ask me. You can unmute the yourself. So just I'll stop the recording now.